Hello there and welcome. This video is on sections 7.1 through 7.3. The main learning objectives for those sections are all about confidence intervals. Specifically, we are going to construct a confidence interval for a population proportion. We're going to construct a confidence interval for a population mean, and we're going to construct a confidence interval for a population standard deviation. So proportion, mean, standard deviation, and then we'd like to clearly explain what a confidence interval actually tells us about a population parameter. Proportion, mean, and standard deviation being three population parameters. Okay, so let's just give a little background on what a confidence interval is and how to think about it, and then we'll do some examples of each of these um, proportions, means, and standard deviations for those things, for those learning objectives. Okay, so the goal of a confidence interval is to use a sample to estimate the approximate value of a value of a population. A measurement of the population is called a parameter, as I mentioned before. So we're going to be using a sample of data to estimate something about the population. For example, we're going to use a confidence interval to estimate a proportion of a population or the mean of a population or even the standard deviation of a population. So these confidence intervals are used to estimate something about a population. The key thing about a confidence interval is that instead of just giving a single value as our approximation, we give a range of values called an interval where we are confident that the proportion or mean or whatever we're measuring lies within that interval. Okay, so we're going to write the interval by specifying the lower limit and the upper limit of the interval. This is going to look like something like x is between the lower limit and the upper limit, or we could use like a math equation saying the lower limit is less than x and x is less than the upper limit. In other words, x is between the lower limit and the upper limit. They can even say something like x is in the interval of lower limit to upper limit. All those are different ways that they may express this interval where we're going to find the population parameter we're looking for. All right, some little heads up. Um, the method, I'm down here in my notes right now, the method and formulas that we use to create a confidence interval changes depending on which parameter we want to approximate. That's why I have separated these into three learning objectives because each one is going to have a different method and a different formula or formulas for calculating the confidence interval. So when you're doing a homework problem, make sure that you are using the correct formulas depending on what the question is asking for, whether it's asking for a proportion or a mean or a standard deviation. All right. There's one other thing that we're going to have to show an example of is that the formulas use this funny symbol, z, with a little like subscript of alpha divided by 2. So the formulas include this or some version of this, and that symbol represents the proportion of data that are above alpha over 2 using a standard normal distribution calculator. Let me do an example of that. By the way, they're going to give you the value of alpha. It's not something you have to figure out unless you just do a simple calculation to figure it out. So here's an example. Suppose we are given an alpha value, a significance level of 0.04. That's alpha, 0.04. So alpha over 2 would just be 0.04 over 2. And 0.04 over 2, you can use a calculator, or you can just take half of 4 cents, which is 2 cents. So alpha over 2 is 0.02. And then we can use our StatCrunch standard normal calculator to find z alpha over 2, which is going to be z of 0.02. And I'll show you how to do that. So I'm going to go over to StatCrunch. I'm going to go to my calculator and just do a normal calculator. It defaults with a standard normal calculator, which means a mean is 0 and a standard deviation of 1. And then I'm going to specify in here, if I can get rid of this right here, let me just hit enter for the moment. I need to specify that the area to the right is no, the area to the right is bigger than 0.02. This is the answer I'm going to get. So the area to the right is 0.02. So I'm going to type in 0.02, and I want area to the right. This the less than sign I need to change to a greater than sign. So I want the area greater to the right to equal 0.02. You can see that's the little area equal to 2%, 0.02. And the value is 2.0537489. And that's the value I have right here. 2.05. I rounded it to 4 decimal places. So the Z value is just from an app like StatCrunch. All right, so that's the basic idea behind confidence intervals. It's going to be an interval where we're confident we can find a measurement of the population, and we're going to do a few of these Z calculations, as you'll see in the different examples. All right, so let's go to our first learning objective, which is to construct a confidence interval for a population proportion. Okay, so here we go. There are formulas, so I'm just going to make sure you have those formulas available. We need a lower limit and an upper limit. That's always going to be how we do our confidence interval. So our lower limit is given by this formula, P minus E. This should say P hat. My PDF maker sometimes leaves off the little hats and stuff like that. So it's going to be P hat minus E, and upper limit of P hat plus E, where E is a formula. It's called the margin of error, and it is Z alpha over 2, our favorite like Z thing, and then we have P hat times Q hat over N. Yeah, my hats are disappearing from my PDF maker, and I don't know how to fix that, but I can just draw them in there. That's how I fix it. Okay, so let's do an example where I show you how to do the calculations. So my example I have here is we would like to estimate the proportion of Californians that support a high-speed rail system. So we're going to get a sample. So in this case, I'm going to pull a simple random sample of 650 Californians, or I'm going to pretend that I do that for the example here. So pretend I find 650 Californians from a simple random sample, and I ask them, do you support a high-speed rail system? And let's suppose that out of the sample of 650 Californians, 3 of them support, right? So 3 of them say, yeah, I'm supporting a high-speed rail system for whatever reason. So what we like to do is we would like to create a 95% confidence interval for the actual proportion of Californians that support a high-speed rail system. So we're going to try to find like a range, an interval of values where we're quite confident that thank you. They were quite confident that the actual proportion of Californians lies between. Okay, so then we're just going to go through these calculations. So we have to find the P hat and the Q hat. The P hat is just the sample proportion. We know that 375 of them support it out of a total of 650. So 375 out of 650, just grab your calculator, you divide that out, and you should get something like 0.5769. That's what I got when I did it. And then for Q hat is just the 1 minus P hat. So Q hat is just 1 minus the 0.5769. Again, calculate it and you get 0.42. So our first step is to find P hat and Q hat. P hat is just the proportion in the sample, and Q hat is just 1 minus that. All right, step number 2. Step number 2 is to find the C and the alpha. C is the confidence interval, and that's typically given to us. So in this particular situation, we're creating a 95% confidence interval. So that tells us that C is 95%. We typically write that as a decimal, which is 0.95. So now we have our C value, and then alpha, just like before, is just 1 minus that value, or the it's 1 minus the C value. So 1 minus, let me do this a little bit clearer here. C is 0.95. So 1 minus 0.95 would give us an alpha value equal to 0.5. So now we know the alpha value is just 1 minus the confidence level. So now we're going to calculate Z alpha over 2. So that was like I did in the previous page. So we get our StatCrunch normal calculator. We want alpha over 2. Alpha, we just found out it was 0.05. That's this one over here. And so alpha over 2 would be 0.05 over 2. 0.05 over 2, according to a calculator, or if you want to math it out yourself, is 0.025. And then that just tells me I need to put 0.025 into my StatCrunch normal calculator. So my StatCrunch normal calculator, I put 0.025, and a greater than sign, and I compute, and there's the little smidgen of 0.025, and that's a value of 1.95996, which kind of rounds to 1.9600. So that's the value right here, 1.9600. So that is my Z alpha over 2 value, and then I put that into my formula. Remember, my margin of error is given by this formula. So I just put it into my little formula here. The E, the margin of error, is the Z alpha over 2 times P hat times Q hat over N. Oh, here's the P hats and Q hats in this time. So the Z alpha over 2, that's the 1.96 number we just figured out. The P hat we figured out from over here. P hat is this value right here, the 0.5769 number. The Q hat, we figured it over here. It's the 0.4239 number. I just plug the numbers in and I do my computation, a lot of computations in a math class, as you know. So I just put all the numbers in, do the math, and I get an E value of 0.0380. So that's my margin of error. And then we just have basically one step left. Our lower limit of the confidence interval is just P hat minus RE, and our upper limit is just P hat plus RE. So here I'm going to do the lower limit is P minus E, which is our P value. Oh, this is P hat. This is our P hat value minus E. Of course, our P hat value is up here. It's the 0.5769 number. And the E, we just figured out, it was the 0.0380 number. So I subtract those two, and I find the lower limit. And then I add those two, and I find the upper limit. So about 0.54 is the lower limit, and about 0.61 is the upper limit. So now we can write out our confidence interval. And I wrote that in terms of a conclusion, which we can put into words. So here's the conclusion. Using the simple random sample of 650 Californians, we are 95% confident, because this is a 95% confidence interval. We're 95% confident that the actual proportion of Californians that are in favor of high-speed rail are between the 54% and the 61%. Remember, 0.54 is the same as 54%, and 0.61 is the same as 61%. So that's our lower and our upper bounds, our lower limit, our upper limit for where we are confident we're going to find the actual proportion of Californians. So again, the conclusion is we are 95% confident that the actual proportion of Californians in favor of a high-speed rail system is somewhere between 54% and 61%. All right, so that is the first example, and a very common example of finding a confidence interval for a population proportion. I have a couple of notes here. Let me zoom out a little bit so you can kind of see more of this on the screen. So the first note is that most software, including StatCrunch, skips steps through 3 through 5. So a lot of the calculations that we had to do in 3 and 4 and 5 are not necessary when you're using an app like StatCrunch. Some of the homework problems ask you for what Z alpha over 2 is, or ask you what E is. So you have to do the computations by hand to calculate those. But to find out the actual confidence interval, a lot of times we can just go straight to the application and it gives it to us. Let me show you how that works. So I can go back to StatCrunch. I'm going to hide this normal calculator. And I'm going to go to Stat. And I'm going to look at a proportion. We're doing a proportion right here, proportion stats. And we have only one sample of data, and we don't have the actual data values. We have a summary. Our summary was we asked 650 people. Some number of them said, yeah, we like high-speed rail. So it's a proportion. We only have one sample of data, and we have a summary of that sample. And then it asks us for the number of successes and the number of observations. Once again, we have successes as those who are in favor. We had, whoops, did I lose it maybe? 375 of them support out of 650. So 375 out of 650. So 375 out of 650 people were asked. We'll do a hypothesis test in a later chapter. Right now, we're doing a confidence interval. We need to have the level of confidence. And for this problem, it was a 95% confidence interval, 95 right there. So we just have to make sure that it says 95 and actually defaults to 95. That's kind of nice. And that's it. We don't need to change anything else. And we're going to hit compute. And here it gives the proportion, sample proportion, that's our p hat, is 0.5769, and that was the same number 0.5769 that we got up here. And it says the lower limit is 0.5389. I'm going to round that to 2 decimal places. So 2 decimal places would be like 0.53, but the next number after the 3 is an 8. So I round that to 54%. So 54% is the lower limit, and the upper limit is 61%. It's not high enough to round, so it's just 61. So we get 54 to 61, which actually matches our lower and upper limit here. So we can get the confidence interval just using an app like StatCrunch offers. Okay, couple other little notes. In order to use these formulas, right? In order to use these confidence interval for population proportion, formulas and apps, we need to know a couple of things. We need to know the sample is a simple random sample, and there's at least 5 successes and 5 failures. And the second thing is we need to know that the population is a binomial distribution. And if you remember from the previous lesson, what we mean by binomial distribution is there's only 2 possible outcomes, yes or no, something like that. All the trials are independent. So when I ask one person yes or no, it does not influence another person that I ask yes or no. So maybe they can't hear each other or something like that. And the probability of them saying yes or no doesn't change. There's no like a news flash in between me asking somebody and then asking somebody else that changes people's opinions. All right, all the information is the same, so everyone has the same chance of answering whatever they were going to answer in the first place. So we need to have those 2 stipulations. It has to be a binomial distribution, and it has to be a simple random sample, and then we can use all these formulas. Last note is sometimes they'll ask you for like, how many people should we have in our sample, right? We want to calculate the sample size n. It's not common, but there is a way of doing it. We would have to know the required confidence level and the specified margin of error. So if you are given the confidence level and a specified margin of error, you can actually say, well, we need a minimum sample size of, 650 or 28 or whatever it's going to be. And there's a formula for it. The formula for it is right here. There's actually 2 formulas. It's this formula here. If we have an estimate for the p hat for the sample proportion, we haven't taken a sample yet because we're trying to estimate how big of a sample we need to do. So if we have an estimate for p hat, then we can use this first formula. If we don't have an estimate for p hat, we can use this formula instead. If we don't have an estimate for p hat, I got to put the hats in some of these. Okay, so on the questions where you're asked, well, how big of a sample size should we be doing? You have formulas for those as well. Again, it involves a z alpha over 2 thing, which is the standard normal calculation. It involves p hat and q hat, which again are just the estimates for the proportion of successes and failures. And then you divide it by e squared. E is given to you because remember, they're going to tell you the margin of error is specified margin of error. So they're going to say E is 0.03 or something. So you're going to put the value of E into the formula and just use your calculator. These are all just numbers that you're going to get, and you're going to calculate the minimum size for N. All right, I'm not going to do an example of that because it's just a calculation thing. If you do want to do an example together, just let me know, and I could run you through the calculation for a particular problem. All right, so that's what I wanted to kind of give you an idea about in terms of constructing a confidence interval for a population proportion. Let's do a similar kind of thing, but now let's construct a confidence interval for a population mean. So we're no longer trying to estimate the population proportion, we're trying to estimate the population mean, and we get different formulas for that. Okay, so for these, we have a lower limit. The lower limit is missing a little mark up here. It's X bar. So X bar minus E would be the lower limit, and X bar plus E would be the upper limit. And E is that margin of error. There's a different, slightly different formula for margin of error than for proportion because each of these different calculations has different formulas. Just kind of keep that in mind. So we have a T alpha over 2, which I'll show you how to get. It's very similar to Z alpha 2. The process is almost identical. And then you have S over root N, where S is the standard deviation of the sample and N is the sample size. Okay, so let's just do an example so I can show you all this, in actual, doing it out instead of just kind of talking around it. So we would like to estimate the average weight of an adult Chinook salmon. So what we do is we catch a random sample, a simple random sample of 134 adult Chinook salmon. So that's the size of the sample. We weigh all these salmon and find out that they have a total weight. So let me do this in green, total weight of 4,900 pounds and a standard deviation of 5.4 pounds. So we did some calculation, we added up the total weight, and we found the standard deviation. Our goal is to create a 90% confidence interval. So this time it's 90% confidence interval. They're going to give you the confidence level. So you just have to read the problem to find out what the confidence level is. This case, this example, we're going to do a 90% confidence interval for the actual mean weight of adult Chinook salmon. So to do so, we are going to use our sample to make a calculation about what the interval of the population would be, where we're going to find the mean of the population. All right, my cat is meowing, so I'm going to pause very briefly. All right, so let me run you through the steps on how to create this confidence interval. So step number 1, we need to find the sample mean. The sample mean is X bar. A little bar there. So our first step right here is to find X bar. X bar is the mean, like the average, which means you have to add up all the numbers together and divide by how many there are. There are 134 fish, 134 salmon, and adding up all the weight gives you 4,900 pounds. We were told that the total weight was 4,900 pounds. So we take the 4,900 pounds of total weight, divide by how many salmon there were, and that will give you the average. Sometimes they just give you the average outright. I did an example here where you had to do a calculation just to make sure that you see how that works. So we take the 4,900 pounds, divide by the 134 fish, and you get an average weight of 36.5672 pounds. Feel free to grab your calculator and check that calculation of 4,900 divided by 134. So this is our X bar value. That is our sample mean. So we're going to use the sample mean to help us estimate the population mean. All right, step number 2 is we need to find the C and the alpha, the confidence level and the significance level. We were given that the confidence level is 90%. Remember the 90% right here. So C is 90% or 0.90. And then to find alpha, you just do 1 minus that. And then 1 minus 0.90 is 0.10. Next thing is we find the T alpha over 2. So just like before, we found Z alpha over 2. We just use the app on StatCrunch to find T alpha over 2. So let's just make sure we know what the alpha over 2 is. Alpha, remember, is 0.10. So we are looking for T alpha over 2, or T 0.10 over 2. 0.10 divided by 2 is 0.05. So we're looking for T 0.05. And that just means we want the proportion to, we want the to the right proportion to be 0.05. So we go to our StatCrunch. Let me hide this. Let me go to my calculator for T. It asks for the degrees of freedom. I do have a little note here that the degrees of freedom right here is my note. Degrees of freedom is always one less than the size of the sample. So we had 134 adult Chinook salmon that we got. So the degrees of freedom are just 134 minus 1, which is 133. So you just subtract 1 off of the sample size. And that's the number you put in for DF, for degrees of freedom. So 134 minus 1 is 133. So let me put 133 in here if my thing will let me. And then here in this little box here, I want to do my my proportion, my amount to the right. Whoops. And the amount to the right was 0.05. Remember the little number down here below Z or below T is the proportion to the right. So 0.05 is what I need to put here, 0.05. Make sure it's going to the right. Yeah, this is backwards. We want greater than, that goes that way. And so here's where the proportion is 0.05, and the value we get is about 1.6563912. And then I rounded that 1.656 number to 4 decimal places, and I got 1.6564. So that's just right off of a StatCrunch. That's the T alpha over 2 using the T calculator versus the Z alpha over 2, which is using the normal calculator. Okay, then we can calculate E. Here's the formula for E. You take that T alpha over 2 number, you multiply by S over root N. So my T alpha over 2 was the 1.65 number I just figured out. The S is given to us. That's the standard deviation of the sample. Remember, the standard deviation of the sample is 5.4. So I just put a 5.4 in there. And then N is the size of the sample, 134. So I do my formula, T alpha over 2 times S over square root N, and punch, 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 calculate, calculate, and I get 0.7727. So now we can finally do our lower limit and upper limit. Lower limit is just X bar minus this E number, and upper limit is X bar plus the E number. So X bar, this should be a bar in this time. Let me put the bar on those. X bar minus, that's supposed to be a bar. My hand shakes with it, so sorry. Doesn't look like a bar all the time. X bar minus E would be my X bar number. Where's my X bar number? Here it is. My X bar number is right over here, 36.5672. And then minus E, here's my E number, 0.7727. So I do the calculation and I get 35.8. So 35.8 would be my lower limit. And then for the upper limit, I do X bar plus E, so the same numbers, but instead of subtracting, I add them, and I get the value of 37.3. Again, just calculations. So now we can, we have our lower limit, we have our upper limit, so now we have our confidence interval, and we can write this in a conclusion. So using our sample of 134 adult Chinook salmon, we are 90% confident, remember 90% confident, that the actual mean weight of adult Chinook salmon is somewhere between 35.8 pounds and 37.3 pounds. That was our lower and upper limits. So that's how we do a confidence interval for a mean. We look at a sample, find the mean of the sample. We do all these number calculations. We end up with a lower limit and an upper limit. And so we say now we are pretty confident 90% confident in this particular example that the actual mean weight of all the population of adult Chinook salmon is somewhere between 35.8 pounds and 37.3 pounds. All right, again, some notes to consider. Sorry if it's kind of small, but I'm trying to get more stuff on the screen. So my first note here is most software, including StatCrunch, skips the steps 3 through 5, just like before with the proportion confidence interval, because the app just gives it to you. So we're doing a T-Stats app because it's the T thing for the mean. And so we can just go to the T-Stats confidence interval, and it will give us these exact numbers. Let me show you how that works. So I go to my StatCrunch. Let me hide this. I'm going to go to stat. Here's my T-Stats. Again, I only have one sample, and I wasn't given the actual data. I was just given a summary. So I'm doing a T-Stats. It asks for the sample mean. Sample mean was, that's the X bar. That's a 36.5672. 36.5672. Sample standard deviation, that was 5.4. Standard deviation of our sample was 5.4. And the sample size, how many pieces of data did we collect here in our sample? 134 salmon were all measured. 134. Once again, choose the radio button for confidence interval. We need to specify the confidence level. The confidence level for this one was not 95%. It was 90%, right? 90%. So let's plug in the 90% here. So 90%, and then we compute. Nothing else we need to do. And it says right here that here's our sample mean, our 36 number that we got. And our lower limit is 35.8 approximately, if I round it, 35.8. And the upper limit is 37.3, it looks like. And those should be the same numbers that I got. Yeah, 35.8, 37.3. So using the StatCrunch T calculator, we can get the confidence interval without having to do a lot of these calculations. Although some homework problems will ask you to calculate T alpha over 2, so you'd have to do the calculation using the steps that I showed you previously. All right, so now we can write out our conclusion. Once again, I actually said this already, but I'll just say it again. Using the sample, we are now 90% confident that the actual mean weight of these adult salmon is somewhere between 35.8 pounds and 37.3 pounds. This is how we do confidence intervals. We get an interval where we are confident that this measurement, this parameter of the population lies somewhere within. All right, we were in the middle of doing some notes. The first note I did was skipping steps 3 through 5. The second note is there are some requirements for using these formulas. These formulas will not give you correct answers unless we know 2 things. The first thing is the sample is a simple random sample. And the second thing is the population is a normal distribution, or we have a sample size of at least 30. So we've got to have a simple random sample, and we have to have either a normal distribution or a sample size of bigger than 30. And that may sound familiar because those are the requirements for a sampling distribution. It's the same requirements. All right, there's a third note, which is similar to the previous page, where there's actually a formula if you want to calculate the minimum sample size, but you'd have to know the confidence level, and you'd have to have a margin of error specified. So you'd have to know a C value and be given an E value in order to calculate the minimum size. It's just a formula. It involves the Z alpha over 2 thing. You just plug in the numbers. There's 2 formulas again. One, if you have an estimate for the population standard deviation, and the other, if you don't have an estimate for the population standard deviation. So depending on the information they give you, they may give you an estimate for sigma, the population standard deviation, or they don't, then there's two different formulas, whichever version you have. We have one more version of confidence interval. So just going back to the beginning, we did a confidence interval for a population proportion, and we just did a confidence interval for a population mean. And our third confidence interval is for a population standard deviation. So we want to somehow estimate the population standard deviation. That's our third version we'll be doing in this chapter 7, this 7.1 through 7.3. Okay, so here we go. A confidence interval for a population standard deviation. Again, a bunch of formulas. Once again, we don't really need to use those formulas because our app will just give us the answers anyway. But I wanted to write down the formulas. There are no homework problems that ask you to go through these individual calculations, but they're here in case you want to do them. You want to verify answers or see what's actually happening. But as far as I can tell, they don't really ask people to do these by hand. So a lot of this is just for your information and to see the parallel computations between all these confidence intervals. But again, I will show you how to do it using the app on StatCrunch. All right, so let's just run to an example before I go through all the little symbols. There's a lot of symbols here. So one of them is like this weird X with a 2 above it and with an R slightly below it. So this is a chi squared. This is actually a Greek letter X pronounced chi. So you may hear people talk about a chi squared test or a chi squared calculation. And that's referring to this particular kind of stuff where we have this big X thing with a 2, and then we have an R and an L for the right side and the left side, so the upper limit, lower limit kind of thing. Again, I don't want to go too much into the formulas themselves since we're not really going to use them too much. So let's do an example. Let me show you an example of how this works. So I went on Google. It says that community college students work an average of 24.8 hours per week. And let's assume that this distribution is normal. We would like to estimate the standard deviation for the number of hours per week that a community college student works. So in order to estimate the standard deviation, we interview a simple random sample of 100 community college students. So this is our sample size, 100 community college students. And we ask them, you know, how many hours per week do you normally work? We take all of that data and we compute the sample standard deviation. The standard deviation of the sample is 5.5 hours per week. And our goal here is to create a 98% confidence interval for the actual standard deviation of the number of hours worked per week for community college students. All right, so let's go through the steps briefly. So step number 1 is we still have to find the information about the sample. So we need to find the standard deviation about the sample in order to estimate the standard deviation about the population. Just like before, we had to find the mean of the sample in order to estimate the mean of the population. Okay, so we're going to find our S, which is our sample standard deviation. In this particular case, they just gave it to us. They said that the standard deviation of the sample is 5.5. So we know it's 5.5. Sometimes they just give us a bunch of data. And if you were given the data, then we could just go to StatCrunch calculator to find the value of S. So we just go to the calculator and find out the standard deviation of that sample. We've done that many times in previous chapters. You can ask me if you want me to go through the steps again. Step number 2, as is before, we have to calculate the C and the alpha. The C is given to us as 98% or 0.98. So we know the C value, and then we have to calculate the alpha, which is just 1 minus the C. So C is 0.98, and alpha is 1 minus 0.98, which is 0.02. And if you wanted to calculate the Z value, it would be Z alpha divided by 2. So we take our alpha value, which is 0.02, divide by 2 to get Z 0.01. I go to my StatCrunch normal calculator and I make sure the area to the right, the proportion to the right is 0.01, and it tells me the number is 2.32. It's just like we did before, right? Same steps. You just go to the normal calculator, keep the standard normal settings, and make sure the proportion to the right is 0.01. And then you do a whole bunch of number crunching, right? So there's these monstrous formulas, but although they look intimidating, they're just a bunch of numbers, right? So it's 1/2 times this square root of 2 times the degrees of freedom. Remember, degrees of freedom are just the one smaller than the sample size. We asked 100 community college students. So 100 minus 1 is 99. So our degrees of freedom is 99. You plug in the 99, you plug in the Z alpha over 2 number. You just plug all those numbers in, you do all this calculation, and you get some values. So this is the chi-squared R and the chi-squared L numbers. And then we can do our final calculation for the lower limit and upper limit by using some more formulas. So again, just plug in the numbers. Hope you don't make any mistakes with the calculations. Just put the numbers in, do all the math, and you get the lower limit of 4.7 and an upper limit of 6.6. And let me show you how to do that using StatCrunch, because I'm not going to go through all the individual calculations. I just like to show you using StatCrunch. So go to StatCrunch, and let me get rid of this thing. And I'm going to do a stat. And for this one, we're looking for standard deviation. Standard deviation is related to variance. So we're going to use the variance stats. If you use a different spreadsheet program, maybe Excel or Minitab or something like that, they may call it variance, or they may call it standard deviation. They're almost the same thing. So in StatCrunch, they call it variance. So I have one sample. I don't have any data. Again, I have the summary. So I do that. My sample variance, that's the variance I got from the sample. Now that's the variance, not the standard deviation. But remember, they're almost the same thing. So the standard deviation of the sample right here, let me do it in, I guess, red or something like that. Or I'll do it black. I'll do it black. The standard deviation of the sample is 5.5. So how do you find the variance if you only are given the standard deviation? Many of you may know the answer, but there are so many formulas to remember in statistics, so you may not remember exactly that formula. I do have on the next page a reminder that the variance is just the square of the standard deviation. So if you're doing population, the population variance is just the population standard deviation squared, and the sample variance is just the sample standard deviation squared. So you just square the standard deviation to find the variance. So we were told that the standard deviation was 5.5 for the sample. So instead of 5.5, wait for my computer to wake up a little bit, 5.5, we have to do 5.5 squared. So I'll do 5.5 squared. You could alternatively just do on a calculator 5.5 squared and find that number and plug it in there. But the variance is the square of the standard deviation. Sample size, we asked 100 peoples. So that's the sample size. You could just verify by looking at the problem again. Oops, previous page. There was 100 community college students that we asked. So that's our sample size. And then we want a confidence interval, and our confidence interval, I believe, was 98%, so 0.98. I'll just double check that real quick. Yeah, 98% confidence interval. Our confidence level is 98%, so we're creating a 98% confidence interval. And that's it. Sample variance, which is the square of the sample standard deviation, the sample size, and the confidence interval or confidence level is 98%. I hit compute, and it's going to do our lower limit, which is about 22.2, and our upper limit is about 43.2. That's the 30.25 there. Okay, so I didn't get the same numbers. So let me try to figure out what I did. I'm going to pause the video and I'm going to figure out what I forgot because apparently it's not giving me the right answer. Okay, so I realized very quickly what I did wrong. So this is correct. I didn't do anything wrong. I'm like, what did I do wrong? Because I didn't do anything wrong. But notice that the readout for StatCrunch tells us sigma squared. It doesn't tell me sigma, it tells me sigma squared. So the lower limit of 22.24 is for sigma squared. So we know that sigma squared is 22.2, whatever. So this number right here, 22.2438, that's sigma squared. So to find sigma, how do I find sigma if I know sigma squared? Well, I have to take the square root of that number. So I'm going to go to my Desmos. I'm going to type the square root, and let's see if I can paste that number in there. Yeah, square root of 22.24, that number that I copied is 4.7 something. And that, my friends, is that number right there. There's the 4.7. So using the StatCrunch app, we have to be careful. I temporarily forgot this, but I'm glad I saw it real quick. We are going to be finding for this particular app the variance, and all you have to do is do the square root to find the actual standard deviation. We're trying to find a lower limit and upper limit for the standard deviation. So once again, StatCrunch didn't give us an estimate for sigma, it gave us an estimate for sigma squared. So to find sigma, we just square root. And to find the upper limit, I just take this number here for the upper limit. That again is sigma squared. So to find sigma, I would just go into here to my calculator and do square root of that number, and I get 6 point, well, if I round it, I get like 6.6. And that's in fact the number I have here for the upper limit. So lower limit would be 4.7, the upper limit is 6.6, according to my calculation when I take the square root of each of those things. All right, so now we have our lower limit and upper limit of our standard deviation sigma. So we can write our conclusion using our sample of 100 community college students. We are now 98% confident that the actual standard deviation of the average hours worked per week is somewhere between 4.7 hours and 6.6 hours per week. So that's how we do a confidence interval for a population standard deviation. Okay, so as I demonstrated, most software, including StatCrunch, skips steps 3 through 5 because the lower and upper limits are just part of the results when using the variance confidence interval app. And then I showed you before, recall that the variance is the square of the standard deviation. So depending on the app you have to that you're using, you may have to like know to square things or to square root things, depending on which direction you're going, right? The population variance is just sigma squared. So sigma is just the square root of the population variance, etc. Sample variance is S squared. So the S is just the square root of the sample variance. Okay, there's one last note I have here is that the requirements in order for these formulas to actually be accurate, we can't just use the formulas anytime we want. We have to have certain conditions or requirements for the formulas to give actual correct answers. So the requirements for a confidence interval for a population standard deviation are, once again, the sample has to be a simple random sample and the population has to be a normal distribution. So those are the two requirements for the confidence interval for a population standard deviation. Okay, so we're almost done with this lecture here on 7.1 through 7.3. The last bullet point, the last learning objective I have is to clearly explain what a confidence interval tells us about a population parameter. So what does the confidence interval tell us about a proportion of the population or a mean of the population or a standard deviation population? So I'll just give you the general idea. Generally, a confidence interval says that using our calculations, our statistical calculations, it finds a lower limit and upper limit. So we used our calculations to find lower limit and upper limit. We are confident that the true population parameter lies somewhere between those two values. How confident are we? Well, that's the specified confidence level C. If you want to be more confident, it changes the numbers a little bit. If you're okay being less confident, change the numbers a little bit. So, I did examples here where you're 95% confident or 90% confident or 98% confident. It just changes the calculations a bit, but we can have any level of confidence that we specify just doing the formulas or plugging in the correct value into StatCrunch. And I had a little note here to see step 6 in each of the 3 examples. So I did try to write out the explanation of what the confidence interval tells us in each of these 3 examples. So in the previous example, I said right here, our sample of 100 community college students tells us we are 98% confident that the actual standard deviation is between 4.7 hours and 6.6 hours, right? That's how you understand what a confidence interval tells us. We are 98% confident that the actual standard deviation is somewhere between 4.7 and 6.6 hours. In the previous example, we were 90% confident that the actual mean weight of adult Chinook salmon was somewhere between 35.8 pounds and 37.3 pounds. So, we're 90% confident that the actual mean lies between those 2 numbers. And in the first example I did, we had a 95% confidence interval. So we're 95% confident that the actual, in this case, proportion of Californians that are in favor of high-speed rail is between 54% and 61%. So it gives us a degree of confidence that the actual population parameter lies between 2 values. In this case, the actual proportion lies between 54% and 61%. Okay, so that is the gist of section 7.1 through 7.3. Thank you for watching to the end. If you didn't skip around too much, again, the idea here was to construct confidence intervals for different measures of a population, specifically a confidence interval for the population proportion, a confidence interval for the population mean, a confidence interval for the standard deviation of the population. And we definitely want you to be able to explain what a confidence interval tells us about a population parameter. And I gave 3 examples of those explanations in my constructing of confidence intervals in the first 3 learning objectives. Okay, so thank you again for participating and watching the video. Please reach out if you have any questions or any comments, or if you just want some more examples, or if you have any what-if scenarios, what do I do in this situation? I'd be happy to help you. I hope you have a wonderful rest of your day and week, and perhaps I'll see you in the next video. Okay, bye now.